The determinant of a square matrix is a number. If that number is non-zero, the matrix is invertible. A determinant also says something about volumes. An example: A is this 3 by 3 matrix. Its rows are called R1, R2 and R3. These rows define a parallelepiped in R3, which we call PR. PR is the set of linear combinations of the rows, where the weights are restricted to values between 0 and 1. If T1 is a value between 0 and 1, all vectors T1, R1 lie on the line segment of vector R1. If we add T2, R2 with weight T2 between 0 and 1, the set is a parallelogram with edges R1 and R2. And if we add T3, R3, the set is a so-called parallelepiped, a sheared block. This video is about the volume of the parallelepiped. The volume can be calculated as the absolute value of the determinant of matrix A. This determinant turns out to be -7, so the volume of PR is 7. This parallelepiped is determined by the rows of A. We know that the determinant of A transpose is the same as the determinant of A, so we can do the same thing for the columns of A. Parallelepiped PK is determined by the columns of A. PK is different from PR, but its volume is the same. It is also 7. This is a theorem. If A is a 3 by 3 matrix, then two parallelepipeds can be defined. One as determined by the rows of A, and another one as determined by its columns. The theorem states that their volumes are equal to the absolute value of the determinant of A. You could use this shorter notation. However, both the determinant of a matrix and the absolute value of a scalar can be denoted by vertical bars, so the combination of both of them might be confusing. Back to the theorem. Why is this formula valid? To answer that, we first investigate the effects of row operations. The first row operation is to interchange two rows. For example, interchanging the first two rows of A gives matrix B. We know that the determinant of B is minus the determinant of A. However, their absolute values are the same. Just the order of the rows has changed, so the parallelepiped determined by the rows of B is the same one as for A, and its volume is the same. So this row operation does not change the absolute value of the determinant, and it does not change the volume. The second row operation is to multiply a row by a non-zero constant k. We know that the determinant is then multiplied by that k. In absolute value, it's multiplied by the absolute value of k. Here we have multiplied the first row by 1.5. The parallelepiped is stretched in the direction of R1. The volume of PB is increased by factor 1.5 compared to that of PA. Factor k can be negative, for example -0.5 as in this figure. The volume is multiplied by +0.5, so by the absolute value of k. Also, the second row operation has the same effect on both quantities. The last row operation is to add a multiple of a row to another row. This does not change the determinant. It does change the parallelepiped though. Here, 2 times the first row is added to the third row. PB is even more sheared than PA. The volume of a parallelepiped is calculated as the area of the base times the height. PA and PB have the same parallelogram as their base, and the height is the same as well. So PA and PB have the same volume. We have seen that the 3 row operations have the same effects on the volume and on the absolute value of the determinant. Now we can prove the formula for the theorem. There are 2 cases. The first is the case that matrix A is invertible. Then A can be row reduced to a diagonal matrix where all diagonal elements are non-zero. Of course, you could row reduce D further to the identity matrix, but that is not necessary here. Look, for a diagonal matrix, The parallelepiped is a rectangular block. The volume is just a product of the length, width and height. This is the same as the absolute value of the determinant of D. So for a diagonal matrix we have proven the expression. And because we can apply row operations to both sides, we can conclude that the expression is valid for all invertible matrices. What if A is singular? Well, then the determinant is 0. We also know that the set rows of A is linearly dependent, so all three lie in the same plane. The parallelepiped has 0 thickness and its volume is 0. This proves the singular case as well, so we have proven the theorem. The theorem can be generalized to square matrices of any size. What does this mean in other dimensions? For example, consider this 5 by 5 matrix. Of course, we cannot draw R5. Still, we can define parallelepipeds as sets in R5. Their volumes can be calculated with the determinant. A special case is for n equal to 2, as in this example. PR and PK lie in R2, so we can draw them. We have a special name for the parallelepiped in R2. It is called a parallelogram. And the volume of a parallelogram in R2 is just its area. These two different shapes have the same areas. Isn't that neat? A determinant can be seen as a volume. For a 3 by 3 matrix, that's a 3D volume in the regular sense. For larger matrices, it gives a generalized volume. For a 2 by 2 matrix, it reduces to an area.